Welcome back to The Explainer. Today we're tackling Chapter 9, Mechanical Properties of Solids, and getting right into the foundational mechanics of the physical world. Do you ever wonder why glass shatters, rubber bounces, but steel holds up entire skyscrapers? Well, it all comes down to the mechanical properties of solids. And honestly, once you understand these hidden rules, it completely changes how you look at the built environment around us.
So let's kick things off by challenging a pretty basic assumption. When you look at a thick steel bar or a massive concrete pillar, is it actually an unbending, perfectly rigid object? I mean, our intuition screams that a solid has a definite shape and size that just doesn't change, right? But the reality? It's way more dynamic. Even the most seemingly indestructible steel bar deforms when you apply a large enough external force. Literally nothing in our physical world is perfectly rigid.
To understand how these materials bend and break, we're taking a micro to macro approach today. Here is our roadmap. 1. The illusion of rigidity. 2. Defining stress and strain. 3. Hooke's law and the curve. 4. The elastic moduli. And finally, 5. Engineering the real world. All right, part 1, the illusion of rigidity. We're kicking this off with a bit of a paradigm shift about what a solid actually is. And to do that, we need to shrink way down to the microscopic level. Okay, so imagine atoms as solid balls and the interatomic forces holding them together as flexible springs. It's kind of the perfect mental model. When a solid is deformed, those atoms are displaced from their stable equilibrium, stretching or compressing those microscopic springs. And just like a literal spring, the second that deforming force is removed, the interatomic forces pull those atoms right back to their original stable positions. And this microscopic restoring force is exactly why materials show elasticity. Take a rubber band, for example. You stretch it, and those atomic springs just snap it back perfectly. But on the flip side, we have plasticity. Think of materials like mud or putty. They just don't have this strong restoring force. When you push them, the atomic structure shifts permanently. It's got no tendency to regain its former shape whatsoever. Moving on to part 2. Defining stress and strain. Now that we've established that solids can in fact stretch and squash, let's lock in the official terms engineers actually use to measure all this. First up, imagine pulling on a solid cylinder from both ends. The internal restoring force that builds up per unit area inside that cylinder, we call that longitudinal stress. It's basically just force divided by area. And the result of that stress, the actual fractional amount that the cylinder stretches compared to its original length, is the longitudinal strain. So, simply put, stress is the internal pushback, and strain is the physical change in length. But we don't just pull things perfectly straight in the real world. Say you put your hand flat on top of a thick book and slide it parallel to the cover. You're now applying what's called a shearing stress. This tangential force physically slants the shape of the object. And that resulting shift, the angular displacement between the top and bottom faces, gives us our shearing strain. And finally, what if we drop a solid sphere deep into the ocean? The immense water pressure applies hydraulic stress completely uniformly from absolutely every direction. Now, this uniform compression doesn't change the object's shape, but it does cause a volume strain. It literally shrinks the physical size of the object. All right, part 3, Hooke's law and the curve. With our vocabulary squared away, let's look at the actual mathematical rule book that governs how these forces interact when we really start ramping up the stress. So, way back in 1676, the English physicist Robert Hooke figured out a fundamental truth about elastic materials. He coined the phrase ut tensio sic vis, which translates to as the distortion, so the force. Basically, Hooke's law tells us that for small deformations, the stress applied to a body and the resulting strain are perfectly, linearly proportional to each other. Let's map this out on a graph, because it actually builds a pretty dramatic narrative for a stretched wire. Initially, the wire perfectly obeys Hooke's law, tracking in a straight line right up to its proportional limit. But if we keep pulling, we hit the yield point, or elastic limit. Past this point, the wire can no longer bounce back. It suffers a permanent set, entering plastic deformation, stretching until it hits its ultimate strength and violently snaps at the fracture point. Now, this specific stress-strain curve is basically a fingerprint. It tells us exactly how a given material is going to behave. If a wire snaps almost immediately after it passes its yield point, that material is brittle, right? Think ordinary glass or cast iron.
But if it stretches out vastly, undergoing tons of plastic deformation before finally breaking, it's a ductile material, just like copper or aluminum. Section 4. The elastic moduli. The major takeaway here is that different materials resist these physical deformations in very specific, uniquely measurable ways. The most famous of these is Young's modulus. It's essentially the ultimate test of how incredibly stubborn a solid is when you try to change its length. Mathematically, it's the exact ratio of tensile stress to longitudinal strain. So a material with a really high Young's modulus requires an absolutely massive amount of force to produce even a tiny change in length. And this table really illustrates the wider physics landscape here. We've actually got three main moduli. Young's modulus measures linear stretch, and shear modulus measures shape distortion. And notice that both of these apply only to solids, because, well, only solids have a fixed shape to begin with. But the bulk modulus, that measures resistance to uniform volume compression, and it applies to solids, liquids, and gases alike. Why? Because absolutely everything can be squeezed if you apply enough pressure. So let's put a real number to this stubbornness. 200. That is the Young's modulus of structural steel, measured in gigapascals. To put that into perspective, aluminum sits at just 70, and your ordinary glass is around 65. Steel massively outperforms almost everything else. It requires immense force just to stretch it by a fraction of a percent. And this unbelievable elastic resistance is exactly why steel forms the unbreakable, hidden skeleton of our modern cities. All right, bringing it home with part 5, engineering the real world. Let's reward all that microscopic math and theory by seeing how we actually apply it to solve massive, real-world problems. Engineers use these precise properties of elasticity to keep us safe every single day. Take a construction crane, for example. To lift 10 metric tons safely, you'd need a solid steel rod about 3 centimeters thick. But a rod that thick is entirely rigid. You can't roll that up. So instead, engineers use dozens of thinner wires braided together into a rope. This maintains that high Young's modulus for strength, but allows for crucial flexibility. Similarly, bridges use eye-shaped eames because that specific cross-section maximizes load bearing while heavily reducing weight and preventing the beam from bending under traffic. Even structural columns use distributed flared ends to spread out compressive stress so they don't buckle. But here's the really wild part. These laws don't just dictate human engineering. They literally dictate the shape of our planet. The base of a massive mountain is actually not under uniform compression. It experiences tremendous shearing stress due to the sheer weight of millions of tons of rock pushing down unevenly. Which brings us to a fascinating planetary limit. Based on the mechanical properties of rocks, if a mountain were to somehow grow taller than roughly 10 kilometers, the pressure at its base would exceed the critical shearing stress of the stone itself. The rock wouldn't just sit there, it would literally begin to yield and flow plastically under its own crushing weight. No way around it. I'll leave you with that provocative thought to remind you that even the most seemingly rigid, permanent structures on Earth, our absolute highest peaks, eventually reach their elastic limit. Thanks for tuning into this explainer, and keep questioning the world around you.